Hey guys, is my audio okay? Because I took off my headset because the record is going to work better if I take off my headset. Can you hear me okay? It's okay? Okay.
Hello.
You guys know this is recording, right?
I do.
Just so you know, you're already recording. I'm going to make you co-host, Ricky, if that's okay, instead of host. If that complicates things, let me know. I haven't had a chance to test the record feature if I make you host.
Mm-hmm.
So I need to test that and I haven't.
All right. Let me try sharing my screen. I can do it.
So you're happy?
Yeah, I should be fine.
So I would go ahead and just get your starting slide up.
There we go.
And just to make sure I'm not crazy, CSU, right?
Yep, Colorado State University.
That part I got. I just needed to make sure I wasn't wrong. How is everybody else doing? Best suggestion I've heard for reading period is to find a book you've already read, like that's a really good friend, and reread it, right? So if you have a book you love and reread it, because it's like a friend giving you a hug, and we all need hugs from our friends right now. That's my fun suggestion, if you're a reader. Because it would also hopefully be a hard copy, and you'd get away from the screen, which would be good. Hey, Aiden, can you show me that you're truly there? And frankly, can you show me that you're truly there?
Oh gosh, frankly.
I'm here for right now, so.
Hey, Stefan. Hey, are you introducing Ricky or am I?
I can do it.
Okay. I have written you down now, Carl. Check for when attendance. Kate, can you show me yourself on the video real quick so I can see you're really there? Okay, thanks. Check for attendance. Zoom meetings are always awkward because there's this time that you would normally be like talking to each other, and it's just like weird and silent.
Yeah. Y'all ever hear of David Goggins?
I'm sorry, I missed that.
Have y'all ever heard of David Goggins?
I haven't.
No.
David Goggins is this insane Navy SEAL. He just goes on the most crazy physical endurance runs ever. He did 4 miles every 4 hours for 48 hours. There's one time he was finishing up a race and he broke all the bones in his feet, but he kept running. That guy was insane.
Yeah, Ravenna does crazy things like that. So I guess it is 3:10, and I'm just gonna be like super efficient, and I'm gonna push us along in all these things. So I'm really excited to start this series. I'm really excited for everybody who to be able to share in all the awesome work that all of our seniors did over the course of their time here, even if we have to do that over Zoom. So Ricky is starting us off here with the very first talk of our 20 talk series. So if you are curious as to the other talks, you can send me an email and I will send you the schedule, or you can find the schedule on the chemistry page, Moodle page. So I think with that, I'm going to turn it over to Stefan to do the introduction, if that works, Stefan.
Thank you. So I'm Stefan Debert. I'm a professor in the chemistry department here at Lawrence, and it's my pleasure to introduce Ricardo Peña. Ricky started out his time here at Lawrence briefly considering a career in medicine. He did some research with Brian Pasecki in the biology department, watching worms move very slowly. And then from there, he took some chemistry classes and decided to go into that direction. He'll talk about some work he did with Professor Laura Anderson at the University of Illinois Chicago here on computational organic chemistry, which is also what I did when I was an undergraduate. And he will be continuing this work, this kind of work, this fall as he enters a PhD program at Colorado State University and plans to work with Professor Robert Patton. What I think is exciting about this work is that after Ricky talks about the work he did at UIC, he's then going to talk about work he did more or less on his own recognizance with the data that he collected. And I think it's an exciting example of sort of not letting someone else dictate the parameters of your research experience, right? And so I'm excited to see what we've got here. So go ahead, Ricky.
Thanks, Stefan. Yeah, as Stefan mentioned, during my summer, I spent my time looking at doing mechanistic analysis of electrocyclization using computational modeling. I worked with Professor Laura Anderson and Dr. Shahid Islam. I learned computational techniques from Dr. Islam, but I spent most of my time with the Anderson group, which specializes in organic synthesis and method development. So, to begin, there's a high commercial demand for new medicine. This is evident when we watch TV and constantly see commercials for antidepressants, allergy medication, or ADHD medication. Currently, we're facing a pandemic with the coronavirus, and in this pandemic, we're searching for drugs that can allow or help people to overcome the virus or the illness quicker, or even not encounter it at all. And finally, the demand for new drugs has grown so large that it's even spread into fictional universes like Supernatural. We even have a movie called Limitless, where the main character takes a drug to make themselves extraordinarily smart. So there seems to be, it's pretty evident that there's a high demand for drugs, and chemists need to keep up with this high demand. So what are the steps in making a drug? First is target identification. The questions that go along with target identification are, what do we want this drug to do? Where do we want this drug to react? How do we want this drug to react? This leads into into drugs that can satisfy these questions. We call these drugs that show the possibility of being successful in a biological system hits or leads. Hit and a lead are synonymous titles. They're the same thing. For example, when Sherlock Holmes finds a clue to a crime, he considers it a lead, as in it's leading him to a conclusion. In the same way, a lead molecule points drug designers to a successful drug. Once we have a hit or lead, we need to tweak the molecule to be tested in a clinical setting. This means that we need to make sure the drug can be administered for the trials in a proper way, and that there will be no issues that can invalidate the tests or the data. Then we need to have a test-ready drug. We need to be sure that the drug doesn't end up harming the participants. And we then need to perform clinical trials. If the drug ends up to be a success in clinical trials, we can then scale up production of the drug. But for every successful drug, there are many drugs that have failed. To give a general example of how many drugs have failed, thousands of drugs are tested and screened. However, only one of those drugs actually make it through to be a successful drug. The reason it's hard to make a drug is that the drug needs to be able to dissolve and get to the signal, a receptor, or to a certain location. Then the drug needs to be able to fit into the signal receptor and change the receptor's shape to cause a signal. Finally, the drug needs to only go to one specific or targeted location. So this limits the total amount of drugs that we can test down to just a few. And these few drugs are the lead or hit molecules. So if we want to increase our chances of a successful drug, we need to increase the number of leads. This means we need to focus on constructing molecules that follow the Lipinski guidelines. Lipinski guidelines are just general guidelines for a good oral drug. The guidelines focus on drug absorption, which we denote as log P, maneuverability, which is incorporated into molecular weight, and fit into the biological signal receptor, which is the molecule's three-dimensionality. I'm going to follow up with the next slides talking about these three focuses. So getting the drug into the body and target the appropriate receptors. The title indicates that there are two parts to making our drug, polar parts and non-polar parts. We'll talk about the polar parts first. To begin, we have our compound inside a pill, and the person in need of the pill swallows the pill, and then the pill dissolves into the body. Then, when the pill dissolves, the drug travels throughout the body using its ability to mix with blood. This ability is called polarity. Polarity is a charge difference caused by the uneven sharing of electrons. The uneven sharing occurs because oxygen hogs the electron from the hydrogen. The hogging is called electronegativity. Electronegativity is increased hogging of electrons by an atom due to increased number of charges at the nucleus pulling on the electrons more. So, blood has water in it, and water is also polar. Things with like polarity mix due to intermolecular forces like hydrogen bonds. And because our molecule likes to dissolve in water, it's considered hydrophilic. So our drug can dissolve in blood, which consists of water, and transport throughout the body. Our drug must be hydrophilic. To reiterate, our drug can dissolve in blood, which consists of water, and transport throughout the body. Due to our molecule being polar and therefore hydrophilic. But then it needs to bind to the cell receptor in a place called the binding site. The binding site serves as a switch to send a signal to the rest of the cell. To bind to the binding site, our drug needs to have a nonpolar component to it. Nonpolar means that the electrons are shared evenly between the two atoms. Nonpolar molecules don't mix with water, so they're said to be hydrophobic. In our binding site, the polar parts point outwards, and the nonpolar parts point in. So the nonpolar parts on our molecule interact with the nonpolar parts in the binding site. The nonpolar parts are essential in this case for selective binding to specific binding sites. In the case of a hormone-like drug, the drug needs to have some nonpolarity to pass through the nonpolar parts of the cell wall. But too much nonpolarity leads to unrestricted binding of the cell to any cell, of the drug to any cell. Overall, the drug needs to have polar and nonpolar parts. It needs to have hydrophobic and hydrophilic parts to succeed in the body. So there's a ratio of hydrophobicity to hydrophilicity, or polarity to nonpolarity, nonpolarity to polarity, that lets our drug dissolve, travel to, and bind to a specific receptor's binding site. This ratio is denoted log P, and log P ranges from +1 to +4. So drug must be more nonpolar than polar to allow the drug to dissolve, but still bind to a binding site. If we look at the range of log P, which ranges from +1 to +4, we see that in the optimal drug-like space, log P is correlated with a molecular weight between 250 and 450 Daltons. When our drug approaches the binding site, it needs to have the right orientation to fit into the binding site. Long molecular chains on a molecule are frequently rotating and changing the overall shape of the molecule. So having a low molecular weight ensures there are fewer moving components, and so there's more of a chance for the drug to have the right orientation to fit into the binding site. In addition to filling the binding site, the drug needs to in addition to fitting inside the binding site, the drug needs to fill the binding site. In this way, it acts like a key that twists the binding site to another position to cause a signal change, or cause a signal. Generally, heterocycles serve as a good drug foundation for constructing a drug around because they appease the Lipinski guidelines. A heterocycle is a ring where one member differs from the rest. Above we have furan, azetidine, and pyridine. The introduction of a nitrogen or a oxygen, hogs electrons from the carbons and introduces a polar side and a nonpolar side to the molecule. The ring part ensures fewer rotating components and therefore more frequent binding in the binding site. Often we find medicines derived from natural products contain heterocycles. In this case, we find will be our desired component is derived from penicillin. So here's our heterocycle. So heterocycles are popular attachments to drug design. They limit issues regarding the Lipinski guidelines and increase the number of leads. But azetidine seems to be the best attachment for drug design. Azetidine is a 4-member heterocycle where N is fixed in one corner of the 4-member ring. It has a low molecular weight, so it can fit into the binding site more easily. It has a positive and negative charge, so there's a polar side and a nonpolar side. Finally, the azetidine has a fold to it, and so it has 3-dimensionality. And in this case, it seems like our azetidine excels under the Lipinski limits. On our azetidine, we can also attach different molecular chains, which we've denoted as R groups. Azetidine has been used in antipsychotics, antimalarials, and anti-inflammatory drugs, where the components that make the drug effective in each scenario are the R groups. Currently, there are 4 different ways to synthesize azetidine. There's a nucleophilic substitution, where an electron-rich atom kicks out a leaving group and closes the ring. Then we have 2+2 cycloaddition, where the pi bonds or double bonds of 2 molecules rearrange to close a ring and form our azetidine. Then we have beta-lactam reduction, in which we start with the beta-lactam, which we've previously seen in penicillin, and we have to isolate from penicillin, to reduce to form our azetidine. And finally, we have a Xerodine expansion, where we start with a 3-member heterocycle, and we expand it to a 4-member heterocycle, or azetidine. Of the yields, 2+2 cycloaddition seems to be the best azetidine synthesis method. But a 2+2 cycloaddition combines 2 molecules into 1 molecule and confines the energy from 2 molecules into 1. So the energy of the molecule, or the azetidine, increases. Then when we force the bond angles to 90 degrees, where atoms in a planar rearrangement like to sit at 120 degrees away from each other, we cause the ring to have a high ring strain, or we form a highly strained ring. Ultimately, the formation of azetidine in this reaction is really unfavorable to nature because of its high energy required for its formation and the high energy it resides at. Along with the long range of yields, this tells me that the reactions don't necessarily or consistently work for different nitrones or different attachments. In other words, we can't make any azetidine that we want. So the Anderson group found an easier way to synthesize azetidines. They started with a Chan-Lam coupling, which couples an oxime with a boronic acid to form a nitrone. This nitrone has 4 bonds to it, where the nitrogen is also attached to 1 oxygen. And this nitrone undergoes electrocyclization to form an azetidine. I won't be talking about Chan-Lam as much in the rest of the presentation. However, the key part is that switching the R groups changes whether we can get an azetidine or not. We're able to switch out the R groups because of the modularity of the Chan-Lam reaction. It allows us to couple different oximes with boronic acids, like we're putting Legos together. Then usually the Chan-Lam proceeds without any issues to form a nitrone. However, the electrocyclization seems to be most dependent on which R groups are attached to the nitrone. So my research focuses on electrocyclization. Electrocyclization is the movement of electrons in concert in a cycle. The electrons can move between adjacent double bonds. So we can think about it as the double bonds as doors swinging and rearranging their location. In which case, electrocyclization concludes with the formation of a new bond and therefore ring closing. Now, my group synthesized over 11 nitrones, 7 worked, and 4 didn't. We wanted to figure out why the attachment of some R groups led to some nitrones cyclizing and others didn't. We wanted a more quantitative explanation for this and ultimately to be able to make a generalization about how this reaction works. As a result, we decided to look at the energy of the electrons in the compounds. So this is where my part in the research comes in. I was tasked with learning how to use Gaussian and then apply what I learned to the reactions that were experimentally tested. Gaussian is a really expensive software that allows me to create molecules in 3-dimensional space and then find the energy of the electrons in the molecules. So it's general background on computation and quantum mechanics. From quantum mechanics, we can depict atoms as having orbitals. And orbitals are electron clouds depicting the probability of an electron being found within a certain volume of space. And from different orientations of orbiting electrons, we can get, and different energies, we can get different types of orbitals. Then these orbitals can be meshed together to form a molecular orbital. The molecular orbital describes the probability of electrons being shared within a volume of space for the whole molecule. More importantly, from my research, the energy of the electrons in the molecular structures can be found from the molecular orbitals. So let's take a look at the process, the calculation process I went through. First, I started with an initial guess of what our molecule could look like in three-dimensional space. I made guesses for all three states of the molecule, including the starting material, the transition state, and the product. I took these guesses from two-dimensional pictures illustrated by the Anderson group. Then I submitted the molecules to Dft Optimization, or just general quantum mechanical optimization. This means that I'm asking the computer to find the lowest energy shape of the molecule. After that, when I've optimized the starting material, transition state, and product, I need to confirm that the optimized transition state belonged to the starting material and product. Once I've secured the optimized molecules, I collected their thermodynamic data. And finally, I was able to analyze or do some data analysis in R. So let's take a closer look at each of these steps. So an initial guess is exactly what it sounds like. I guessed at what the lowest energy shape of the molecule at the starting material, transition state, and product would look like. I took the 2D structures identified by the Anderson group and applied the atoms in three-dimensional space. I guessed the bond angles and the rotation of the attachments. Unfortunately, this method is the most successful method for finding optimized molecules. Then optimization would rotate bonds and shift electrons until the molecule was in its lowest energy shape. Computationally, to confirm our transition state, I ran a calculation which allows the transition state sitting at a higher energy above the starting material and product. I allowed this transition state to unfold to its lowest energy shape, which could look either like the product or starting material. This confirmed that I had the transition state, whether or not I had the transition state. After calculation, I retrieved enthalpy and Gibbs free energy from the output files. Other data could also be obtained from the files, but I only focused on retrieving the thermodynamic data. The change in Gibbs free energy between starting material and product indicates the likelihood of a reaction proceeding. The change in enthalpy indicates energy released from forming a bond or the energy needed to break a bond. The change in Gibbs free energy from the starting material to the transition state is called the activation barrier, which is the energy the starting material needs to convert from its initial point to the product. Our goal in using Gaussian is to get the thermodynamic values, Gibbs free energy, enthalpy, and solve for entropy of each state of the molecule. Then we can see if there are any trends within the thermodynamic values that explain why some nitrones undergo electrocyclization, while others don't. So the change in Gibbs free energy from the starting material to the transition state is the activation barrier. The change from the starting material, or the change in Gibbs free energy from the starting material to the product is the change in the ground state. The overarching goal of my part in this research project is to use Gaussian to further characterize the mechanism found by the Anderson group. This will allow drug chemists to use the reaction more efficiently and create more drugs containing Xerodine. And with more drugs containing Xerodine, there will be more hits. And if there are more hits, the chances of finding biologically successful drugs increases. So in my research process, I compiled data on the Gibbs free energy of the starting material in the gas phase and in methanol, of the transition state in the gas phase in methanol, and of the product in gas phase and methanol. From that, I was able to gather the activation barrier, the change in Gibbs free energy, and also the change in enthalpy for the ground state and transition state, or activation state, transition state, and the change in entropy for the ground state and transition state. I was also able to gather the twist of the molecule from the starting material to the transition state. And this twist is called the dihedral angle. I won't be talking so much about the dihedral angle at all. The idea was to identify a trend from these thermodynamic values, especially the transition states. At this time, I concluded my research under the UIC SROP program, with only having secured the ground state thermodynamic values. So after the SROP program, I stayed and volunteered with the Anderson group because I felt that there was still more to be done. I wanted to secure the transition states. So after getting the transition states, I searched for thermodynamic trends. More specifically, I searched for a trend in the activation barrier. So in this graph, I've plotted the different nitrones, along with their activation barriers, where red or no indicates nitrones that didn't undergo electrocyclization. X indicates nitrones that weren't synthesized, but were made within Gaussian. And yes, or blue, indicates nitrones that did cyclize in synthesis and did produce an Xerodine. So as you can see, the no molecules are spread out evenly throughout the whole, throughout the decrease in activation barriers, which tells me that there isn't a trend in activation barrier. However, I still recognize that the activation barrier had something to do with nitrones cyclizing. At this point, I was completely stumped. So I gave a vague description of my dilemma to another professor I was meeting with. And he pointed me to looking at the top 2 highest occupied molecular orbitals. So I looked there. Turning my focus to the top 2 highest occupied molecular orbitals, I focused on the difference between the 2 highest occupied molecular orbitals of the starting material and the transition state. I wanted to find how the difference between the highest occupied molecular orbitals changes from the starting material to the transition state. So I found the difference of the difference, which I've called the gap difference. And plotting the gap difference with the corresponding nitrones, I saw that 2 groups formed. 2 groups of cyclizing Xerodines, nitrones formed. The first group falls below this negative 17.6 kcal per mole gap difference threshold. And the second group is much above this threshold. So what type of structures are in the 2 groups, and how do these structures differ? In the first group, we predominantly see withdrawing groups in the R3 and R4 positions. The electron withdrawing groups could present an electron pulling effect, which seems to lower the second highest occupied molecular orbital of the transition state, and therefore determine whether a nitrone cyclizes or not. Yet, the group 2 still cyclizes much above this threshold. The molecules in group 2 all have electron donating or electron dense groups at the R2 and R4 positions. It seems like the electron donating groups push electrons into the center of the nitron, and cause the double bonds to break and rearrange to form the Xerodine. So in summary of the grouping, group 1 has structures that contain electron withdrawing groups at the R3 and R4 positions. These molecules have a gap difference below the negative 17.6 kcal per mole threshold. However, group 2 has electron donating groups at the R2 and R4 positions and cyclize much above the negative 17.6 kcal per mole threshold. So R groups have some sort of influence on gap difference and ultimately electrocyclization. But more research is needed to identify conclusively how the R groups lower the energy of the second highest occupied molecular orbital in the transition state, and figure out the difference between the second highest occupied molecular orbitals and how those alter the activation barrier, or figure out how the difference in the second highest occupied molecular orbitals and not the activation barrier is responsible for electrocyclization. So in the future, we need to figure out how the R groups change the gap difference and how the gap difference influences the transition state of the molecule and ultimately causes electrocyclization. So we do this by gathering further experimental and computational data to see how R groups influence the two highest occupied molecular orbitals. In these groups, I've attached an electron donating group to the R4 position to see how the R4 position plays a role in electrocyclization. I've replaced that with a electron dense group to once again get another idea of how the R4 position plays a role. Then we've attached a larger R group on there to see how sterics can play a role in electrocyclization, or it can play a role in influencing the second highest occupied molecular orbital. Then we want to see if we can enforce some sort of directionality from pushing group to a pulling group. And we want to see if we can use that directionality to push the nitrone towards electrocyclization. We've also used the reverse. We've eliminated an electron withdrawing group in this situation to see if the electron dense group up here can still cause electrocyclization. And finally, we want to see if we can eliminate a lot of the electron pulling, electron withdrawing effects, and see if the nitron still cyclizes or not. Ultimately, we need to figure out what groups of on a nitron will promote or inhibit nitron electrocyclization. Then we can more efficiently apply or optimize the reaction such that any series of custom nitrones will form a Xerodine. Finally, in increasing the number of customized nitrones, we can increase the number of contenders for a successful drug and increase our chances of coming across more than one successful drug to be produced. So if I can make this reaction easier to use, drug chemists can apply it. Apply it more frequently to create more leads and increase the chances of finding a successful drug. I'd like to give thanks to Lawrence University and USC and my research group, Professor Anderson, Laura, Tyler, there's me, Robert, and Abdullah isn't pictured. Thank you. Any questions?
That's me clapping really loud for everybody.
Okay. Very, very silent.
Okay. If anybody has any questions, you can either raise your hand and I'll call on you. You could chat to me, or you could just unmute yourself and ask the question, whatever you feel most comfortable with. Somebody? So I guess I can start. Okay, Stefan, go ahead.
Yeah, I like this work. This is great. I know we've talked about this a little bit, and we've talked about some of the other things that you looked at and did not see a correlation with, right? So I think that I remember you talking about we're looking at charge distribution and Mulliken values, and you weren't able to find a correlation with that, right? Did you look for any kind of correlation between the orbital, the size of the orbital coefficients on the ends of those carbons, so carbon 1 and carbon 4?
I
Might be.
don't think I did. At that time, I didn't really have the. It wasn't until I encountered the professor who I asked about, or to help me a little bit, that I found out you can actually look at for the orbitals in Gaussian. I had no idea prior to then.
Sure.
But I hadn't gone into looking at the coefficients.
Other questions? I have a very probably.
Aiden is trying to raise his hand, but he can't find the raise hand button.
Oh, I'm
Yeah.
sorry. Go ahead and Aiden, just talk then.
Okay, I have a question about the methodology in which you use Gaussian, because you say first you construct or you make this, I guess, educated guess of the structure of the molecule, and then you optimize that structure with Gaussian.
Yeah.
What's the point of making a guess if all you're going to do is then optimize it to its lowest energy conformation?
Yeah, it's as simple as you have to start somewhere. You can use the optimization calculation, but if you have no molecule to use the optimization calculation on, well, you know.
Well, I guess what I'm trying to say is like your guess doesn't have to be like, you just have to like put the molecules in Gaussian and then it'll just do it.
Yes. Yep.
So if I can jump in here, this is usually like a two-step process. I don't know if it still is, but I know when I was doing this work, your first job is to make sure you've got the correct geometry. And that is an iterative process. You can't use too high of a level of theory or it's going to take forever and a day. And then once you get a geometry that you're satisfied with, now you run another calculation at a much higher level of theory and you say, okay, freeze the geometry, I'm good there, but give me the energy. And that's where you're going to get the more accurate thermodynamic properties. Is that right?
Yeah.
Yeah.
For my scenario, so we used, I'm going to throw some random jargon on there, B3 LYP 6-31. I guess a very loose idea is the longer the number, 6-3113, right? The longer the number, the higher order of calculation. We generally just stuck with 6-31 because it was fast, and I really didn't have, we didn't have the time or the space on the supercomputer to run higher levels of calculations. There were a lot of people using it.
Do you want to give us the density functional theory summary in 2 minutes? No is an acceptable answer.
That is the answer that I will give.
Yeah, so the key with B3LYP is that we can talk about orbitals, but B3LYP is a DFT method, density functional theory. So it's not actually starting from orbitals like other methods are. DFT kind of comes at it from a physicist perspective and says, well, where are the electrons? Because that's what we care about, which isn't quite the same as trying to solve for your orbitals.
Interestingly enough, we stuck with B3LYP, and B3LYP seems to be the most successful successful function at optimizing molecules. However, I did notice that there's another type of basis set that I want to use, M06, which takes into account quasi-harmonic oscillations. These are not accounted for in my calculations. However, the patent group has produced software called Good Vibes, it's a cool name, where you can input your output files. you can input your Gaussian files, and they will immediately solve and produce corrected values for the quasi-harmonics. I just thought that was really cool.
Other questions?
How long does it take to run the calculations normally?
Yeah. So when we submit a calculation to the supercomputer, I generally submit the calculation for 24 hours. This is just a range, a time limit for the calculation to finish within. At the bottom of the output files, you'll see total processing time. Generally for the ground state calculations, maybe an hour, maybe not. Fairly quick. If it's a simple molecule, maybe even a few seconds. The transition states, on the other hand, those take a while. And this is why my time at USC, for the SROP program, I hadn't gotten the transition states, because the transition state calculations took so long to optimize or to secure. And that's assuming that they succeed. A lot of the times the transition state guesses would fail, and I'd have to rearrange and try again. I could try different methods, like finding an intermediate structure between the starting material and the product. However, that calculation, it rarely ever succeeds, unfortunately, and it seems like guessing is our best chance. Yeah.
Just to go off of that, do you want to talk a little bit about the structure that interacting with the shared resource of the supercomputer involved? Like kind of just a sense of like job submission and all that stuff, because I think many people maybe have never been exposed to that.
Yeah. So if you're lucky enough to get a computer with Gaussian, somehow, wink, wink, you can make a very, very small setup file on your computer. Now, what you need to do is you need to take that setup file and you need to send it somewhere else to be processed. So essentially, a supercomputer is a giant processor and file storage location. So you transfer your file through internet and through the wireless system. You transfer your file to your file on the supercomputer. And then you're put into a batched system, into a list of until your time comes up. And when you're cycled through and your time comes up, then your calculation is pulled out of your home folder on the supercomputer and then processed. And once it's done processing, it will submit back into your home folder, to which you can access through the internet and pull out onto your local computer.
Yeah, so you got to get in line. You got to get in line to use the computer, and if you use it too long, people yell at you.
Yeah. Also, right near the time where I was submitting the most transition states and needed data, the supercomputer underwent maintenance, which ended up being elongated for another like 2 weeks. And so, yeah, I had to switch the computers I was doing processing on.
Any other questions?
Did you use any other computational techniques to like compare it to your DFT results, or is DFT a robust enough method where you just kind of trust it?
DFT seems robust enough for the uses that for the way we're using it. We're just looking for the computation to pair up with our experimental data and just point us in some sort of direction as to why our reaction may work or may not. We're not necessarily trying to figure out any underlying theoretical question here. So for our purposes, it was robust enough.
And it's worth putting a point on the fact that we're not looking for absolute values here. We're looking for relative, right? We're looking for trends. There's no magic number we're trying to hit.
Any other questions? Well, I guess then everyone on mute, because I think we at least need to hear one clap. I appreciate the talk, and I know it's hard to go on Zoom, so thank you for all being here to listen to the Zoom talk, and thank you, Ricky, so much for giving a great first talk. I'm going to go ahead and stop recording. You don't have, everybody doesn't have to leave, but we're not going to record anymore.